Behind every victory lies a hidden battle. But what happens when the greatest minds wage war with science itself? A silent battle unfolded in the shadow of war, not on the front lines but in the laboratories. When the world stood on the edge of darkness, a powerful alliance arose, not just of soldiers and generals, but also of scientists, engineers, and inventors. During the chaos of intensive wartime, research and development led to the invention of multiple technologies, such as guided missiles, radar, nuclear weapons, mass-produced penicillin, and proximity fuses. These scientific discoveries helped provide wave and surf forecasting, advanced weather, and anti-submarine warfare. The British Prime Minister Winston Churchill once declared, "Give us the tools, and we will finish the job." As scientists uncovered the secrets of atoms and refined missile guidance systems, they walked a fine line between innovation and responsibility. These scientific advancements were born in a time of urgent need and would carry forward into the Cold War. Welcome to Historical Digs, where we dig out the secrets from the annals of history. Niels Henrik David Bohr, father of quantum mechanics. In the chaos of war, while most battles were fought on the ground, one unfolded in the world of atoms, where a brilliant mind held the keys to untold power and perhaps even peace. Niels Henrik David Bohr was born in Copenhagen, Denmark, on October 7, 1885. He is known as one of the fathers of quantum mechanics and made significant contributions to quantum theory and atomic structures. For years, people have read about him and watched documentaries and films detailing his story. But do you know the crucial role he played when the world stood on the brink of destruction? Niels Bohr's journey into the world of science began early. At just 7, he started his education at the prestigious Gammelholm Latin School. By 1903, he began his undergraduate studies at the University of Copenhagen, dedicating himself entirely to physics under the mentorship of Professor Christian Christensen, the university's only professor of physics at the time. Bohr's natural curiosity and dedication set him on a path toward becoming one of the most influential minds of his era. In the 1930s, when the Nazi regime captured and controlled Germany, spreading its shadow to every corner of the country, scholars found themselves in a dangerous situation. Many Jewish and political opponents were forced to leave their homelands. In 1933, the Rockefeller Foundation created a fund dedicated to protecting refugee scholars and promoting intellectual freedom. In May 1933, Bohr flew to the United States, where he met Max Mason, the president of the Rockefeller Foundation. He discussed initiatives of the program that could help scholars who were evacuated from Germany. Bohr opened the doors of his institute to shelter the refugee scholars, providing them temporary jobs, securing Rockefeller fellowships, and helping them find placements around the world. As World War II loomed, Bohr's thoughts turned to the potential applications of uranium-235. He understood that this isotope could theoretically make an atomic bomb more powerful, and in his lectures in Denmark and Britain, he touched on the concept. Yet, even then, Bohr doubted that extracting enough uranium-235 for such a weapon was technically feasible. Little did he know that the world was on the brink of a scientific breakthrough that would forever change the course of history. By 1943, while in England, Bohr joined a project that would change the world, the Manhattan Project. But Bohr's approach to atomic science was different. He recognized the incredible destructive potential of nuclear technology and questioned its long-term impact. While many were focused on developing the atomic bomb to end the war, Bohr saw the atomic bomb from a different perspective. He is credited with saying, "We are in a completely new situation that cannot be resolved by war." Throughout his time in the Manhattan Project, Bohr urged openness between nations regarding nuclear technology. After the war, Bohr continued his quest for peaceful nuclear cooperation, founding the Open World Initiative, which promoted international collaboration and regulation over nuclear weapons. In a world eager for power, Niels Bohr dared to champion peace, proving that sometimes the greatest courage lies in urging restraint. Now, imagine detecting the aircraft of enemies before they could even attack. What a change that will bring to war. Robert Alexander Watson Watt, father of radar. Robert Watson Watt was born on April 13, 1892, in Brecon, Angus, Scotland, the youngest son of the carpenter and cabinet maker Patrick Watson Watt. Watson Watt claimed he was a descendant of the famous inventor and engineer of the practical steam engine, James Watt. Continuing down the path of his ancestor, he had a vision to invent technology of radio waves that could detect enemy planes before they reached the horizon. And it came true during World War II, especially in the Battle of Britain. Robert Watson Watt began his education at Damaker Primary School and continued at Brecon High School. He went on to study at University College, Dundee, which was affiliated with St. Andrews University, and graduated in 1912 with a degree in electrical engineering. His academic success earned him an assistantship from Professor William Petty, who further encouraged him to pursue studies in radio technology, known then as wireless telegraphy. Petty introduced Watson Watt to a postgraduate class focusing on the physics of radio frequency oscillators and wave propagation, setting the foundation for his future work in radar development. In the early 1930s, he recognized the potential of radio waves to detect distant objects and envisioned a system that could locate enemy planes before they appeared on the horizon. Initially, he developed this technology to detect thunderstorms, helping aviators navigate dangerous weather conditions. But as Europe edged toward war, his work took on a new direction. In early February 1935, while leading the radio department at National Physical Laboratory in Teddington, England, Watson Watt submitted a memorandum to the British government elaborating how radio waves could be harnessed to detect aircraft. He quickly followed this with practical demonstration, and by July of that year, he had developed a system capable of consistently locating aircraft up to 140 kilometers or 90 miles away. This innovation evolved into the chain-home radar system, which operated at frequencies between 22 and 50 megahertz, significantly lower than the radars being developed before World War II. Watson defended his choice of frequency with his analogy, cult of the imperfect. This meant inventing functional technologies quickly rather than being perfect. By September 1938, the first chain-home radars were fully operational around the clock. Later in the year, when World War II erupted, the UK had 18 radars in place. This statistic massively increased to 53 by the war's end in 1945. The chain-home system played a crucial role in the Royal Air Force's success against the German Luftwaffe during the Battle of Britain in 1940, and in recognition of his contributions, he was knighted for it in 1942. He summarized his philosophy with, "Give them the third best to go on with. The second best comes too late. The best never comes." As the war proceeded, Watt's radar technology became a huge success and a cornerstone of Britain's defenses. Radar towers were built as an invisible shield against German air raids. The invention of radar was pivotal for enhancing military defense during World War II. These radar systems could detect Luftwaffe bombers long before they reached their targets, allowing the Royal Air Force to scramble fighters in time to intercept them. However, Watt's radar technology didn't just win battles. It changed the nature of warfare itself. His story reminds us that sometimes the most powerful heroes are those who see what others cannot. But speaking of the aircrafts and air raids, let's talk about the scientist who actually developed the rockets. Wernher von Braun, father of the American space program. Wernher von Braun, a man whose dreams of reaching the stars turned into a weapon that shook the Earth. In the depths of World War II, one man's fascination with reaching the stars became one of war's most powerful and controversial innovations. Wernher von Braun was born on March 23, 1912, into a wealthy aristocratic family. His mother, recognizing his curiosity about the natural world, fostered his interest by giving him a telescope during his confirmation in the Lutheran Church. This gift ignited a lifelong fascination with astronomy and space exploration, laying the foundation for his eventual career in rocket science. In 1920, his family relocated to Berlin, but Braun struggled academically, particularly in physics and mathematics. A pivotal moment came in 1925 when he discovered Hermann Oberth's influential work, The Rocket into Interplanetary Space. Motivated by his challenges with math, he dedicated himself to his studies and eventually excelled. While studying at the Berlin Institute of Technology in the early 1930s, von Braun joined the German Society for Space Travel, where he began collaborating with Hermann Oberth on researching into liquid-fueled rocket engines. Driven by a belief that their work would advance human knowledge, he dedicated himself to exploring the potential of rocket science. However, with World War II escalating, von Braun's research veered to a darker path. The German military wanted rockets not for exploration, but as weapons. He graduated in 1932 with a Bachelor of Science in Mechanical Engineering and continued his education at the University of Berlin. By 1934, Braun earned his PhD in physics from the University of Berlin. His dissertation, titled About Combustion Tests for Military Security Reasons, focused on the theoretical studies and experimental work related to 300 and 660-pound thrust rocket engines. In December of 1934, under the dictatorship of Adolf Hitler, Braun's team, which had expanded to include another engineer and 3 mechanics, successfully launched 2 rockets that ascended vertically over 1.5 miles or 2.4 kilometers. However, the landscape had changed. The German Rocket Society had dissolved, and rocket testing was prohibited by law, leaving military channels as the sole avenue for research. A significant military development center was established in the village of Peenemünde, located in northeastern Germany along the Baltic Sea. Under the leadership of Dornberger as the military commander and Braun as the technical director, the facility became a hub for innovation. Here, they successfully showcased liquid-fueled rocket aircraft and jet-assisted takeoffs, while also developing the long-range ballistic missile A-4 and the supersonic anti-aircraft missile known as Wasserfall. The propaganda ministry rebranded the A-4 as the V-2, which stood for Vengeance Weapon 2. The V-2 was unlike anything the world had ever seen. It could reach supersonic speeds, traveling high into the atmosphere before striking its targets without warning. By 1944, these rockets rained down on London and other European cities, causing massive destruction. Von Braun reportedly reflected on the weapon's devastating power, saying, "The rocket worked perfectly, except for landing on the wrong planet." This remark, later noted by his colleagues, reflected the conflict he was experiencing, caught between his scientific aspirations and the harsh reality of war. While the V-2 was a tool of destruction, it was also an engineering marvel. It was powered by liquid-fuel rocket engines and employed gyroscopic guidance, marking a significant leap forward in missile technology. Braun was still holding on to his vision for exploring space despite his contributions to the Nazi war effort. After the war was over, von Braun and his team were captured by the United States as part of Operation Paperclip, a program that sought to bring Germany's top scientists to America before the Soviets could reach them. The United States recognized von Braun's expertise and saw potential beyond his wartime contributions. However, in 1973, Braun was diagnosed with kidney cancer during a regular medical checkup, which could have been controlled by medical intervention, but the cancer spread to his pancreas, resulting in Wernher von Braun's death on the 16th of June, 1977. What do a physicist, a radar pioneer, and a rocket scientist have in common? They changed the course of World War II and our future forever. During World War II, a few imaginative scientists changed the battlefield in certain ways that would echo through history. Niels Bohr, the brilliant physicist, grappled with the potential of atomic science, urging restraint even as the destructive power of nuclear technology became apparent. Sir Robert Watson Watt, the father of radar, created an invisible shield that allowed Britain to defend its skies from relentless air raids. And Wernher von Braun, the rocket engineer whose dreams of space exploration turned into tools of war, laid the foundation for modern rocket science. Together, these men pushed the boundaries of technology, each driven by their unique vision, each impacting the course of the war and the shape of our future. Thank you for joining us on this journey through the powerful minds that shaped World War II. If you find these secrets of Allied science and technologies intriguing, then don't forget to subscribe and come back for more History Digs.